Hello everyone. In this class, we'll try to learn about what is pulmonary ventilation. Some of the important terms in pulmonary ventilation are ventilation and minute ventilation. Ventilation is a dynamic process that moves air in and out of the lungs, whereas minute ventilation is the volume of air that enters the lung each minute. This is the product of tidal volume and respiratory rate. This is also called as minute respiratory volume. If tidal volume is 500 ml, the respiratory rate is 12 per minute, the minute ventilation is 6 liters. Therefore, minute ventilation is equal to tidal volume into respiratory rate, that is somewhere around 6000 ml per minute. Normally, minute ventilation in adult is 5 liters to 10 liters per minute. As the respiratory rate varies from 10 to 20 per minute. However, tidal volume also varies with age, gender, body composition and metabolic activity. In children, tidal volume is 3 to 5 ml per kg of body weight, and respiratory rate is also high in children. Expired minute ventilation is the amount of expired air per minute at rest. Is the same as minute ventilation as inspired air and expired tidal volume, that is the amount of air inspired in or expired out in quiet breathing is same. Alveolar ventilation. The volume of air that actually reaches the alveoli per minute is called as alveolar ventilation. It is denoted by VA. The ultimate goal of pulmonary ventilation is to continually renew the air in the gas exchange area lungs, that is alveoli, where air is in close proximity to pulmonary blood. To know the volume of air that takes part in alveolar ventilation, first the dead space of the volume is subtracted from the tidal volume and then the volume is multiplied by breathing frequency. Dead space. Dead space is defined as a space within airways that do not allow gas exchange with pulmonary capillary blood to occur. The tidal volume air occupies the respiratory tract that consists of conducting and respiratory airways. The fraction of tidal volume that occupies the conducting airways does not take part in gas exchange. For each 500 ml of air inhaled, about 150 ml remains in the conducting zones, that is airways, which is not used in gas exchange. This volume of wasted air is known as dead space volume. Thus, dead space is the space within airways where gas exchange with pulmonary capillary blood does not occur. Since the dead space is due to the structural arrangement of the airways, often it is referred as anatomical dead space. Due to the anatomical dead space, out of 500 ml of tidal inspiration, 350 ml of air enters the alveoli. Thus, the normal dead space volume is around 150 ml. The ratio of dead space volume to tidal volume in normal health is 25 to 30%. Thus, normally 30% of the minute ventilation does not participate in gas exchange. Physiological dead space. Some amount of inspired air in the alveoli does not participate in gas exchange. This happens as some alveoli, due to various reasons, have little or no blood supply. Therefore, air in the alveoli also becomes part of wasted air. The volume of air in these alveoli is referred as alveolar dead space. The sum of the anatomical dead space and alveolar dead space is called as physiological dead space. So, physiological dead space equals to anatomical dead space plus alveolar dead space. The alveolar dead space is negligible in normal individuals. Therefore, in normal healthy individuals, anatomical dead space is almost equal with the physiological dead space. However, in various lung diseases, alveolar dead space volume becomes high, in which the physiological dead space is more than the anatomical dead space. Measurement of dead space. The volume of dead space may be estimated by three methods. One is Radford formula, and second and third are single breath carbon dioxide and nitrogen techniques. Bradford formula predicts anatomical dead space of the individual. The anatomical dead space of an individual in milliliters is equal to his weight in pounds. Thus, for a person with a body weight of 150 pounds, that is 70 kg, the dead space is 150 ml. However, this prediction is fairly reliable for healthy individuals, but not in patients with respiratory problems. Single breath carbon dioxide technique. The volume of dead space, that is VD, is usually measured by single breath technique that uses Bohr's equation in the form of gas such as carbon dioxide. Carbon dioxide used because it is almost absent in the inspired air and its alveolar concentration is same as systemic arterial blood. So according to the Bohr's equation, the dead space is equal to uh, FAX minus FEX, that is alveolar concentration and expiratory rate concentration of the gas into ventilation divided by concentration of that particular gas in the alveoli. So here VD is the volume of the dead space, VE is the volume of the expired air, FAX and FEX represent concentration of gas in the alveolar air and mixed expired air respectively. As the alveolar concentration of gas is same as arterial blood, FAX replaces FAX. By using the gas equation for this estimation, so dead space is equal to partial pressure of carbon dioxide uh, in the artery minus the concentration of carbon dioxide in the expired air into uh, the ventilation divided by partial pressure of carbon dioxide in the blood. This can also be determined by single breath nitrogen technique. The subject sitting comfortably breathes room air calmly for few breaths. Then he is instructed to take a deep breath from normal mid inspiration, during which he is switched to uh, over a pure oxygen source where he takes a deep breath with pure oxygen. The subject is then asked to expire slowly and steadily to maximum so that the volume expired is his vital capacity. As he expires, a simultaneous record is made of volume flow rate and the percentage of concentration of nitrogen in the expired air, which is plotted as a graph. So this is the plotted graph, shows a different phases: phase 1, phase 2, phase 3 and phase 4. Here the nitrogen levels with the lung volume are estimated. You can see uh, the nitrogen levels gradually increases as the air is expired, then it becomes plateaus, okay, until it reaches the uh, residual volume. When the subject takes deep breath of pure oxygen, all the air in the dead space is replaced with oxygen, while the oxygen in the alveoli mixes with nitrogen and carbon dioxide in the residual volume. The initial gas exhaled in the phase 1, which fills the dead space and therefore does not contain nitrogen. The phase 2 is the mixture of dead space and alveolar gas, and the phase 3 is alveolar gas. Phase 3 ends at closing volume, which is the lung volume above residual volume when airways in the lower parts of the lungs starts closing due to the less transmural pressure in these dependent regions. In phase 4, content of expired air increases, which ends at residual volume. The dead space volume in the volume of gas expired in phase 1 and the volume of expired till mid portion of the phase 2. The dead space can be calculated from a nitrogen curve obtained from the single breath nitrogen test in two ways: by constructing the equivalent dead space alveolar air boundary and by planimetry measurement. Construction of equivalent dead space, the alveolar boundary. Dead space is filled with pure oxygen prior to expiration. Therefore, the appearance of nitrogen in the curve indicates the air coming from alveoli. The boundary between dead space air and alveolar air is S-shaped because of some degree of mixing of alveolar gas with the dead space air. However, an equivalent sharp boundary is constructed in such a way that the amount of nitrogen in the dead space area is equal to the amount of nitrogen in the alveolar air section. The dead space volume is then calculated as the volume of expired up to this line and is read from the volume recording. Planimetry measurement. The area representing dead space volume and the area representing total volume expired are estimated with the help of planimeter. The total area in the graph represents VE, and hence the dead space volume from the corresponding area is determined by simple proportion. Alveolar ventilation. The volume of air that actually reaches the alveoli per minute is known as alveolar ventilation. To know the volume of air that takes part in alveolar ventilation, first the dead space of the volume is subtracted from the tidal volume and then volume is multiplied by breathing frequency. Okay, so this is how you measure dead space by single breath nitrogen test. Okay, so this is the amount of nitrogen which is expired. The concentration of nitrogen which is expired, it gradually increases and then it plateaus. Okay, and this area of uh, the planimetry, which consists of no nitrogen, is dead space. Significance of alveolar ventilation. Alveolar ventilation represents the amount of air reaching the alveoli. This is the air that takes part in gas exchange. Even in the absence of lung disease, if anatomic dead space volume is increased due to any cause, alveolar ventilation decreases. For example, a patient on mechanical ventilator, alveolar ventilation decreases due to increased dead space volume by tubing, etc. In such patient, if minute ventilation remains constant, the alveolar gas exchange suffers. Physiological significance. In rapid and shallow breathing, though the minute ventilation does not change much, alveolar ventilation grossly impaired because of the air inhaled is utilized to occupy the anatomical dead space. Therefore, the patient with rapid and shallow breathing develop hypoxia and hypercapnia. In contrast, a subject with deep and shallow breathing will have adequate alveolar ventilation, though the minute ventilation does not change. Such subjects have alveolar ventilation even greater than the subject with normal breathing. Thus, to improve alveolar ventilation, it is important to increase the depth of breathing than to increase the frequency. In fact, during moderate to severe exercise, a trained athlete achieves the target alveolar ventilation by mainly increasing the depth rather than the frequency of breathing. How do you measure alveolar ventilation? Alveolar ventilation is easy to calculate if dead space volume is known. However, the dead space volume is not easily determined in a human subject. Alveolar ventilation is calculated in the pulmonary function laboratory from volume of expired carbon dioxide per minute and fractional concentration of carbon dioxide in the alveolar gas. Because no gas exchange occurs in the conducting airways and the inspired air contains essentially no carbon dioxide, all of the expired carbon dioxide originates from the alveoli. So thus we CO2 is equal to ventilation into the concentration of carbon dioxide in the alveoli. Therefore, VeCO2 is the volume of carbon dioxide expired per minute and FaCO2 is the fractional concentration of carbon dioxide in the alveolar gas. Rearrangement of this provides alveolar ventilation equation. So alveolar ventilation is equal to VeCO2 divided by FaCO2. The carbon dioxide concentration in the alveoli can be obtained by sampling the last portion of the tidal volume during expiration, the end tidal volume which contains alveolar gas. Alveolar ventilation reflects PaCO2. It is important to note that the inverse relationship exists between the alveolar ventilation and partial pressure of carbon dioxide. Here in this diagram you can see the alveolar ventilation and its relation with the alveolar carbon dioxide, which has the inverse relationship. If alveolar ventilation is halved, the alveolar PCO2 will double. Clinically, the adequacy of alveolar ventilation is an index of arterial PCO2. An increase in partial pressure of carbon dioxide reflects hypoventilation, and decrease in uh, partial pressure of carbon dioxide in artery reflects hypoventilation. Okay. So this diagram represents the inverse relationship between alveolar ventilation and PCO2. Okay. So when alveolar ventilation reduces from 10 liters per minute to 5 liters per minute, the carbon dioxide levels rapidly increases. Clinical abnormalities of ventilation. Hypoventilation. Hypoventilation occurs in many conditions. Usually they are categorized into depression of respiratory centers by diseases or drugs, which is called as central hypoventilation, and failure of ventilatory apparatus, that is peripheral hypoventilation. Hypoventilation leads to decreased PaO2 and increased partial pressure of carbon dioxide. Alveolar ventilation, hypoventilation occurs mainly in exacerbation of chronic lung diseases such as asthma, chronic bronchitis, and emphysema. Depression of respiratory center also occurs in head injuries or by drugs such as barbiturates and opiates. Neuromuscular disorders that weaken the respiratory muscles, example myasthenia gravis, poliomyelitis, acute polyneuritis, and tetanus. In hypoventilation, hypoxia occurs due to the decreased oxygen supply, and hypercapnia occurs due to the decreased carbon dioxide removal. Hyperventilation usually occurs due to the stimulation of respiratory centers. However, the voluntary hyperventilation and exercise induced hyperventilation are common physiological causes of hyperventilation. Excess removal of carbon dioxide in hyperventilation results in respiratory alkalosis. Okay. So this is the relation between the ventilation with the alveolar PO2. Okay. And it is linearly increases with ventilation alveolar PO2 and remains plateau at particular point. So this is in brief regarding the ventilation. Thank you.